Hi guys. Okay, so we are going to finish the lecture that we did not finish in class over soil basically, and then I'm going to record the lecture 32 that we didn't do either. So we left off with mineral transport. So we're still dealing, or we're going back to xylem up. But minerals are different from water because minerals actually have to be actively transported. So there's two parts of the xylem. There's the tracheids and the vessel elements. Most of the inorganic nutrients are absorbed from the soil, and then they are transported up from the root to the leaves by the xylem. And then they're going to be used for photosynthesis, except for carbon dioxide, of course. Carbon dioxide goes directly through the leaves, if you remember. So you can see in this picture, the roots are going to take in oxygen for cellular respiration, and they're going to create ATP that way, so that the minerals can then be absorbed using that ATP and take up through the xylem. Now there's a difference between beneficial nutrients and essential nutrients. Beneficial nutrients are going to help a particular plant grow better, and those are going to be different for all plants. So if something is beneficial for you, it helps you, right? Well, it's the same thing with beneficial nutrients. Silicon for equisetum, which is the plant we looked at in primitive plants, and sodium for sugar beets are just two examples. Now, essential elements, on the other hand, these are required for growth. So if something is essential to your life, you need it. You absolutely need it 100%. So macronutrients, macro means big, so these are the nutrients that plants need in large quantities. Carbon, hydrogen, and oxygen are those three big ones. 95% of the plant's dry weight are actually those three elements, and they get these elements from water and carbon dioxide. Others, you've got potassium, nitrogen, phosphorus, sulfur, calcium, magnesium, but the thing with these is they must be in the ionic form, because only their ionic forms are soluble in water, and they have to be soluble in water. Micronutrients, micro means small. So micronutrients are things that are needed in smaller amounts. So iron, boron, manganese, copper, zinc, chloride, molybdenum, these also have to be in their ionic form because, again, those are soluble in water. Now, the three things that determine if something is essential or not, and this is important, it's on your test, they have to have an identifiable role, which basically just means that they have to specifically do something, and we have to know what that something is. So whether it's helping the plants get access to more carbon or whatever it is, we have to know what it is. They cannot be substituted. So you can't say, well, carbon is an essential element, but we can just give them gold instead. You can't do that. They can't be substituted. And then, of course, the last one is deficiency causes the plant to die. So without it, they're going to die, hence the essential part of it. So essential elements are not only important for those plants, but they're important for us, the consumers who eat the plants, because how many minerals are available to the plants determine the quality of the minerals that we get from the plants. So for example, plants that are nitrogen deficient, the grains that they produce are not as high in food content that's good for us. So the pathway is the same as water, except minerals are actively transported, so they need ATP. But what this does is it gives the plants the ability to concentrate some of the minerals. So some of them are 10,000 times more concentrated in the root than they actually are in the soil. So the solutes are going to be dissolved in water, and then they're going to enter the xylem if they make it through the Casparian strip of the endodermis. So like I said in class today, that endodermis has the Casparian strip, which is like the regulator. So it has to be actively transported through the Casparian strip, and then it will get to the xylem. So the pathway is the same. They still go through the root hairs, they go through the cortex, they go through the Casparian strip in the endodermis to get to the xylem, but actively transported. Okay, so what determines what minerals are available? Well, the soil does, of course. So it's important to keep essential minerals that are inorganic nutrients in the upper topsoil. So they have to be in close proximity to those root hairs. Remember, the root hairs are what absorb things. Soil actually has horizons, they're called, and that's just the different layers of soil. So the humus and the topsoil, or the O and A horizons, are the two that plants really have access to. So typically we have sand, silt, and clay in soil all mixed up together. Clay is normally negatively charged and kind of holds on to anything positively charged. But negatively charged minerals are not bound as tightly by clay, so they're going to be less available to plants. Because of this, they happen to drain out of the soil, and that's called leaching. So when we lose nutrients to the soil because they drain out, it's leaching. Now the ideal composition, which is number 16 on your portfolio, what type of soil is best for plants? Loam, L-O-A-M. And loam, what is its composition? It is made of 1/3 sand, 1/3 silt, and 1/3 clay. So it's a combination of all three things in equal amounts. The reason that this is good is because it retains water, but still has good drainage because there's enough air in there. It provides enough air spaces because, again, remember the roots need oxygen for cellular respiration, and it provides enough water for the root to absorb, and water is needed for photosynthesis. So it holds on to water enough, yet there's good enough drainage and air pockets so that we can perform respiration and we can still hold on to some water. Now this is what you need to write for number 16. So sand only drains water too fast, so that's going to lower how much water is available. Clay drains water too slow, so that's going to lower how much oxygen is available. So again, an equal mix of sand, soil, and clay. Sand, silt, and clay is the best option. So how can we increase mineral uptake? There's a few ways. Of course, we have our mutualistic relationships. We talked about bacteria and root nodules of plants that are going to fix nitrogen for them. We've also talked about fungus roots, mycorrhizae, which will increase water and mineral absorption because they grow around the roots of the plants and they increase the surface area, which makes them more efficient. Parasitic, also Haustoria. These are produced by mistletoe, daughters. They're going to tap right into the xylem and phloem to steal those nutrients from those plants. And then in nitrogen poor soils, carnivorous plants have actually evolved. And these are like sundews, pitcher plants, Venus flytraps. But they can actually capture insects and then digest them and take their nitrogen and other minerals for their own use. Hormones allow plants to respond to environments. So plants do have hormones. They can respond to the environment. Now these can be transported from the xylem or the phloem or even from cell to cell. Auxin is a particular hormone that is responsible for what's called tropism. And tropism is just growth towards or away from a particular stimulus. Positive tropism is towards the stimulus. Negative tropism is away from the stimulus. So gravitropism is gravity. Plants exhibit negative gravitropism because if you put a plant on its side, it will actually grow up away from gravity. Thigmotropism, again, that is touch. So you can touch some leaves on some plants and they will actually close up. So here you can see a plant growing on its side for gravitropism. Then you have thigmotropism. Phototropism, plants will grow towards the light. So they have positive phototropism, for example. Okay, number 17 just says to list the 4 ways that plants respond to light. So the red light response is the first one. All you have to do is write red light response. So the phytochrome system is going to act like a biological switch. It's going to control growth so it can slow it down if light conditions are not optimal. So if they don't have enough access to light for photosynthesis, they will slow the growth down. It can also trigger germination and seasonal responses. The blue light response is the next one to list. Phototropins are protein-based receptors that are responsible for mediating the phototropic response. So as I had said earlier, plants respond to light positively. They grow towards it for the most part. They respond to blue light. So phototropism is that directional response that allows plants to grow towards, sometimes away from, but usually towards the light. Positive phototropism, again, is towards it. Other responses are leaf opening and closing, chloroplast movement, and then the stomata opening and closing. And then the other two that you list are photomorphogenesis and photoperiodism. So photomorphogenesis is when the development of plants and the growth of plants is in response to light. So basically, the plant's not going to grow too big if they do not have enough light or space. So it's going to be regulated based on how much light they have. If they have enough light, the plant is triggered to grow bigger unless the space is confined. But this is what allows them to do that. Photoperiodism is the ability to track time using light. So plants can kind of tell the time of day and the time of year by sensing and using the different wavelengths of sunlight. So for winter, kind of touching on those seasonal changes, how winter, the days are shorter, plants can kind of tell that and will adjust accordingly. Finally, the defense mechanisms. Number 18 is list 4 of them. You can pick any 4 of these and list them. You do not have to explain them, just list them. So leaves can often have thorns or hairs, and that's going to discourage predators because they just don't like eating them, or thorns may hurt them. They can have toxins like morphine, quinine, Taxol, caffeine. We all know how those impact our body and make things speedy, I guess you would say. Cysteamine is a chemical that's going to make the animal sick and disrupt their digestive enzymes so they cannot digest what they eat. And then volatile molecules is what I had mentioned in class before, where whatever the herbivore is, the plant will release volatile chemicals, and that will bring the predator of that herbivore so that they won't eat the plant. Instead, they're going to have to try to get away from their predator. And then there's also something called the hypersensitive response. Basically, if damage happens, the plant will seal off that area. So if you have local cell death, it will be contained in that particular area. And that's actually it for this presentation. So I will go ahead and record chapter 32 to finish off the portfolio. So you should have had 16, 17, and 18 answered from this video. All right, bye.